Hi guys. So today we're going to talk about the College Board Unit 1.5, atomic structure and electron configuration. So a reminder of our electronic structure. For this unit, what we want to emphasize is that we have a positive nucleus and we have negative electrons on the outside. And that nucleus, its amount of charge is going to be based on the number of neutrons that are present. So here we have a magnesium and a beryllium. So we can see the magnesium is going to have a larger positive charge in its nucleus than the beryllium is. We also know that electrons, although have the same equal charge no matter where they are, the further away they are from the nucleus, the less pull they have on each other between the nucleus and the electron. The electrons that are on the inside, we call those core electrons, and the electrons that are on the outer energy level, no matter how far they are, we call those the valence electrons. So an important part of electron structure is Coulomb's law. And this gives us the force that is between 2 points that have charges. Now, 2 points that can have charges, we can be talking about the electric force between a nucleus and the electrons that are satelliting that nucleus, or we can be talking about two atoms and their electric force between each other. So looking at Coulomb's law, we will not actually be using any calculations for Coulomb's law. We just want to understand its concept and be able to apply it to different situations. So here we see F stands for that electric force. We do have a constant, Coulomb's constant, that you can easily look up and is also on your equation sheet. You do not need to memorize that. And then we have Q1 and Q2. Q1 and Q2 stand for the amount of charge that is found in each of those different points that we're comparing. And then R is the distance between those two charges. So this force that we are analyzing with Coulomb's law can either be a force of repulsion or a force of attraction. So here we see we have, we're comparing two nuclei, two different atoms that are near each other. We have the same distance, the same R, but here they are going to repel each other because they are like charges. And here we're talking about a nucleus and an electron, and they are going to be attracted to each other because they are opposite charges. So we know that we can use Coulomb's law to calculate this force, but we need to keep in mind whether that force is one of repulsion or one of attraction. So here we are comparing magnesium and beryllium again. And remember, the magnesium nucleus has a pretty good charge with all these protons there compared to beryllium with only 4 protons. We can also compare the distance here. We know that the center of the magnesium nuclei is going to be a much further distance from its most valence electron compared to the beryllium. So reminder that ionization energy is the quantity of energy required to remove an electron from an atom or ion in its gaseous phase. So ionization energy is caused by this Coulomb's law, this relationship between the charges and the distances. So ionization energies, as we move further out on the energy levels, the less ionization energy there is, the lower it goes, because it's easier to remove those electrons. And it is harder to remove each electron after that, because you're getting a positive charge. And so that ratio of electrons to protons is being offset. So here we are taking a look at ionization energies being compared across our third period here, our third energy level. And so this first column is the energy to remove one electron, the first electron. And this is to remove the second electron and the third, and so on. So here, if we look at sodium, it is much easier to remove the first electron than the second electron. And that's because sodium is going to have a positive charge there. Also, and we'll talk more about this in another unit, it has a full energy ring after that, right? Magnesium, we see, easier to remove the first electron than the second, and then even harder to remove the third. We also see that as we go down our column here, it is harder to remove that first electron because we are adding protons. So we have a greater nuclear charge here. Obviously, the electron charge is not changing, but the nucleus is getting a greater charge. So if we were to go back to Coulomb's law and think about this, K times Q1, Q2 over R squared. So in this situation, we are increasing a top number. And so if we're increasing the top number, then our electric force is going to be higher. If we increase the distance, meaning that the electron is further away from the nucleus, and we increase the distance, then of course F is going to be smaller. So the further away an electron is from the nucleus, the less force there's going to be. That is more important than shielding effect. A lot of students like to think of shielding effect, that there are so many electrons. I'm going to actually go back a slide here. So that when we look at the atom, shielding effect is these core electrons. And people like to think that the larger or greater number of core electrons there are between the nucleus and the valence electrons, the less attraction there is between those valence electrons and the nucleus, when in fact it's really about the distance away. Coulomb's law that we have, that R factor, the distance there on the bottom. So the greater the distance, the less force there will be. However, if we increase the protons, we're increasing the charge in one of our points, and so that charge is going to be greater. So we've increased the numerator, and so our force is going to be higher. Let's give a look here at this one. Look at the diagram below. Which electron, A, B, or C, is the easiest to remove, and justify your answer in terms of Coulomb's law. So let's take a look here. First off, we have comparing our nuclei here. Here we have a nucleus that has 2 protons. So this is going to have a greater Q1 to Q2. So this is going to increase the top part of our Coulomb's law. So it's not that one. So the stronger the nucleus, the harder it is to remove this electron. And then, so now we're comparing B and C, and now we're talking about distance. We're comparing R. So obviously C has a greater distance between the two than B, so that gets rid of this one. So this has the smallest Q, or electrical charge, and the greatest distance. So our denominator is big and our numerator is small, so it's going to be C.